All right, today we're going to tackle two of the biggest players in precalculus, the common and the natural logarithms. If you've ever felt a little lost with these, don't worry. You are absolutely in the right place. We're going to clear it all up.
You've been there, right? Staring at an equation with log or ln and thinking, hold on, where did the little base number go? It's a super common point of confusion, and today we're going to solve that mystery for good.
So here's the big secret. Log and del(n) aren't some brand new, crazy concepts. The best way to think of them is as special nicknames. They're just shortcuts that mathematicians gave to the two logarithmic bases they use all the time. And here's the rule, plain and simple. Whenever you see log with no base written, it's secretly or, by convention, a base 10. And anytime you see ln, that's just the cool way to write log base e. That's it. It's just a notation change to save some time, but you've got to know it.
Okay, let's put these two side by side. It's the best way to really see what makes them tick and where you're going to run into them.
So here we go. In the left corner, we've got the common log. Notation is log x, and its base is 10. You'll see this all over the place in science and engineering. Think pH scales in chemistry or decibels for sound. And on the right, the natural log, lnx. Its base is that famous, kind of weird number e, which is about 2.718. This one is the absolute superstar of calculus and anything involving continuous growth, like populations or finance.
And check this out. This shows a really fundamental property. A logarithm is always asking the same question. What power do I need to raise the base to get this number? So for log of 10, it's asking, 10 to what power gives me 10? Well, that's just 1. Same thing for ln of e. E to what power gives me e? It's 1 again. A log of its own base is always 1. Remember that.
Theory is one thing, but let's actually see how this works with some real problems. We're going to walk through a few examples so you can see this notation in action. Let's start with something straightforward. Evaluate ln of e to the 5th power. Okay, remember what ln means. It means log base e. So the question is really, what power do we need to raise e to in order to get e to the 5th? When you say it out loud like that, the answer is just staring you in the face.
Yep, it's just 5. The natural log and that exponential base e are inverses of each other. They basically undo one another, leaving you with just the exponent. Pretty neat, huh?
Okay, next up, log of 1,000 plus log of 0.1. Don't let it intimidate you. We just handle each piece one at a time. First, log of 1,000. That's base 10, so 10 to what power is 1,000? That's 3. Then, log of 0.1. 10 to what power is 0.1, or 1/10? That's -1. Now, all we have to do is add our two results together.
And 3 plus a -1 gives us our final answer, 2. See? When you break it down, it's totally manageable. For our last one, we're actually solving for x. ln of x equals 0. The trick here, the key to everything, is to get rid of that logarithm. And we do that by rewriting it in its exponential form. Since ln is base e, this equation becomes e to the power of 0 equals x. And we all know that any number, other than 0, raised to the power of 0 is just 1. So our solution is x equals 1. Using that conversion to exponential form is a huge tool for solving these kinds of equations. Okay, before we wrap this up, I need to point out a huge, and I mean huge, mistake that students make all the time. If you can avoid this one, you'll save yourself so many headaches. This is so important. When your eyes see ln of x, your brain can't think of it as L times n times x. That's not what it is. It's a single thing, a function, an operation, just like a square root sign or sine of x. It's doing something to x. And because it's a function, you can't just divide by ln to get x by itself. That's like trying to divide by a square root sign. It doesn't make any sense. To undo a natural log, you have to use its inverse. You have to use the exponential e as the base, just like we did in that last example. So we know what they are and how to work with them, but why do we care so much? Why do base 10 and base e get this special nickname treatment? Well, let's look at why they're so important. Here's a perfect real-world use of the common log. The pH scale. You've definitely seen it in science class. The formula is literally pH equals the negative log of the hydrogen ion concentration. Because it's a base 10 log scale, a small jump in the pH number, say from 6 to 5, is actually a 10-fold increase in acidity. That's base 10 doing its job in every single chem lab. Okay, base 10 makes sense.
right? Our whole number system is base 10. But what about e? Why is a logarithm with this weird, unending decimal base of 2.718 considered natural? What's so natural about it? And here's the payoff. The real reason the natural log is so special is calculus. When you get to calculus and you start learning about rates of change, or derivatives, you'll find that the derivative of ln x is the beautifully simple function 1 divided by x. Any other base gives you a much uglier, more complicated formula. It's because of that elegance and simplicity that the natural log becomes the go-to for pretty much all of higher-level math. So what might seem a bit strange right now is actually setting you up to make your life way, way easier in the future.